Okay. There. Good afternoon again, and we are starting with the chapter, continuing with chapter 18. We talked about naming aldehydes and ketones. We talked about physical property, solubility, intermolecular forces, common name, IUPAC name, some common uses or industrial importance and uses in outside of the chemistry lab where aldehydes and ketones are used. There are two aspects left. One, how to prepare these compounds. Second, how to, what are the chemical reactions for these compounds? First, we are going to look at the preparation. So for the preparation of these compounds, to prepare it, because this chapter covers both aldehydes and ketones, there are a lot of back and forth going, preparation of aldehyde, then preparation of the ketone, and then a next method for preparation of either one of them, because they are kind of similar, because the pattern is the same, is going to help if you look at the same type of reaction for both of them. Like if you wanted to do oxidation of alcohol, oxidation of secondary alcohol would give you ketone. Oxidation of primary alcohol would result in aldehyde. With oxidation meaning removing, okay? When you say oxidation in organic chemistry, so you are removing two hydrogens or adding oxygen, okay? Or oxygen bond. The hydrogens that are removed when you have alcohol, one is the hydrogen from OH, and the other one is the hydrogen from the same carbon that carries the OH. So when you remove these two hydrogens, then carbon needs to have a double bond. I'm sorry, 4 bonds. So we have to give carbon a double bond oxygen in order to satisfy 4 bonds. Because when you remove H here, you're not removing a bond, but when you are removing the H from carbon, so removing H from OH is not removing a bond from the carbon, but removing hydrogen from the carbon is removing a bond from the carbon. Then you end up with 3 bonds only. So a double bond to oxygen is going to satisfy the 4 bonds. Now we have 2 bonds to oxygen and 2 other bonds to 1 carbon each. When you have a primary alcohol, you remove hydrogen from the OH and you remove hydrogen from the same carbon that carries the hydrogen, the OH bond, and it gives you aldehyde functional group. So aldehyde, we talked about the CHO last class, is basically CO, double bond and hydrogen, both attached to the carbon. Now, the oxidizing agent. There are a lot of reagents in organic chemistry too. You have to memorize all your reagents. And know that which one to use when. First of all, from the first chapter, like when we talked about chapter 11, I start chapter 11 asking you to list, give me a list of oxidizing agent and tell me which one is a strong oxidizing or if it's a weak oxidizing. So sodium bicarbonate, sodium dichromate, if you go back to your notes from chapter 11, is known as a strong oxidizing agent. PCC or pyridinium chlorochromate is a weak oxidizing agent. So it is the weak oxidizing agent, but sodium dichromate is a strong oxidizing agent. What happens if you use strong oxidizing agent for primary alcohol If you use a strong oxidizing agent like sodium dichromate, CR207, with H2SO4, this can go to next step of oxidation, and it can give you a carboxylic acid. So if you want to stop in the aldehyde, that's this chapter, basically you want to make aldehyde, you have to use weak oxidizing agent, because if you use a strong oxidizing agent, a primary alcohol would go to aldehyde, but then it would go second step of oxidation and would change to carboxylic acid. That's why it's important to use PCC, which is a weak oxidizing agent, and it would selectively oxidize primary alcohol to aldehyde, and it will stop there, because if you add PCC to aldehyde, there would be no reaction. Okay, so if you add PCC to aldehyde, there would be no reaction. PCC to secondary carbon, would it react or not? If you use PCC here, it's going to take to ketone. Yes, PCC is strong enough to oxidize alcohol, but is not strong enough to oxidize aldehyde. So secondary alcohol can react with PCC, and it gives ketone as well. Any questions? Questions? Okay, we are still in the preparation of alcohols, and we want to find out what are the other methods that you can prepare aldehydes or ketones. Ozonolysis, and when you talk about ozonolysis, which is the oxidative cleavage of alkene, your reactant is alkene, so you need to know that your reactant is alkene. Your reagent is ozone, and you want to make sure to use dimethyl sulfide as a solvent. Because if you don't use this dimethyl sulfide, your aldehyde is not going to stay aldehyde, it can go to carboxylic acid. So you would use the dimethyl sulfide with the ozonolysis as a solvent. So what's going to happen, actually, dimethyl sulfide would gain oxygen. So O3, it's you see that there are three oxygens there. When you have three oxygens, one of these oxygens, this reaction is oxidative cleavage. Cleavage means that you would cut through carbon-carbon double bond. And oxidative, meaning that you would add a oxygen, double bond oxygen to carbon on the left side, double bond oxygen to carbon on the right side. So you have three oxygen. What's going to happen to the third oxygen? The third oxygen would react with sulfur, and it will give you sulfoxide. So you get dimethyl sulfoxide, DMSO. If you remember, we use this as a aprotic solvent in SN2 type reaction. So it's the DMSO is abbreviation for dimethyl sulfoxide. Is a liquid, but dimethyl sulfide would oxidize because it's like a reducing agent itself, is going to be oxidized to DMSO. So basically it's going to consume the third oxygen. Otherwise, that third oxygen can go here and give you carboxylic acid. So it's very important to use dimethyl sulfide with the ozonolysis, because you want to keep this aldehyde as aldehyde. So in oxidative cleavage, what you're looking for, the carbon-carbon double bond, it would be cleaved through double bond, and you get a double bond oxygen on each carbon. Now, what happens to the product? Do you get ketone or aldehyde? It depends on the R groups. So if you have a CC double bond, with a CC double bond, you get 4 other groups attached to it. To each carbon, there would be 2 groups attached. If those 2 groups are carbon, or in general, you would represent as R. If there are R groups, then you would get, as a result of oxidative cleavage, you would get ketone. Okay? If one of them is hydrogen, the other one is carbon, you would get aldehyde. If both of them are hydrogen, then you would get like formaldehyde. And formaldehyde can be oxidized to CO2 if you have a strong oxidizing agent, in like hot permanganate if you have, or the ozonolysis, it can oxidize further to carbon dioxide. But if you have one hydrogen, one carbon, you would get a aldehyde on one side and ketone on the other side. If the alkene that you are using is a symmetrical alkene, let's say you have ethyl group here, and then you have ethyl group on the other side. If you have symmetrical alkene, when cleavage takes place, and the cleavage is as a result of ozonolysis, that means that you are doing oxidative cleavage, the two products that are formed here, they're identical. So this is one of the best ways to prepare like ketone, because it's a symmetrical alkene, and both of these are same. So you get per molecule of alkene, you get 2 molecules of ketone, and you don't have like impurities. But when you get ketone and aldehyde, a mixture of ketone and aldehyde, then you will have to worry about the next step. And the next step is to separate them from each other, because if you have a mixture of 2 or 3 different compounds, it's not going to be, you don't have pure product. So in a chemical reaction, you don't want to have, if possible, you don't want to have mixed product, because if you have mixed product, then you have to be worried about purification. That goes back to design of the experiment. So if you have the choice of what alkene you are using, it's best to get a symmetrical alkene. Depends on what product you're asking you to prepare, and that is called like a retrosynthesis. So you have to look at what product is being asked to prepare, and say that the carbon that carries the CO double bond now, it used to be part of a CC double bond. This carbon that carries the CO is supposed to be part of the CC double bond. So anything that is attached here as a R prime and double prime is going to stay. They like ethyl group, methyl group, whatever group they are, it's going to stay. And whatever the of R is, it just copies down or carries down, and there is no change. So you kind of go backward, trying to see what reactant should you use in order to get this product. But if you don't have a mixture of 2 products, if it's just one product, try to mirror this and get a symmetrical alkene. So oxidative cleavage of alkene can generate either aldehyde or ketone, depends on number of the R groups that you have on the CC double bond. Next type of reaction is Friedel-Crafts reaction. In the Friedel-Crafts reaction, we learned that in chapter 17, that if you do alkylation, you get alkyl benzene, and if you do acylation, your product is going to be ketone. So you start with the benzene ring or a substituted benzene ring, and then you're adding acyl group. And to get the acyl group in, the best compound that you could get the acyl group, because it's the COR, you can get from carboxylic acid. So if you have COOH, you can get the acyl group. But carboxylic acid is not very reactive. If it's not very reactive, because it's a stable, it's going to slow down the reaction, because it's not very reactive. But acid chloride or acyl chloride, this is a very reactive acid derivative, and it's going to react faster. The catalyst that is used here is the aluminum chloride. Aluminum chloride would remove the Cl with the pair of electron, and then you get the plus charge on the carbonyl group. And that's going to make it a strong electrophile, and is going to react with the benzene ring. If we do have electron donor group here, then the acyl group, it can go to either ortho position or it can go to para position. So you get a mixture of two products. We have another example here. In this example, the acyl group is coming from a para-nitrobenzoyl chloride. So basically you remove the chloride and then this is your RCO. Okay. After Cl leaves, this is going to give the plus charge to carbon, and that makes it a strong electrophile. This is going to react with the benzene ring, and where it's going to attach is that okay, this is the acyl group. Any of the hydrogens can be targeted. So it's going to attach to any of the carbons from the benzene ring, because your benzene ring is not substituted benzene ring. And you get your ketone. So the purpose of this reaction is to form a ketone. It can form a ketone from Friedel-Crafts acylation reaction. Any questions? So ozonolysis, Friedel-Crafts acylation. For Friedel-Crafts acylation, you can only get ketone. You cannot get aldehyde unless you are using formaldehyde. Like if you use formaldehyde, you can get aldehyde. Okay. Ozonolysis, it depends on the R group that you have on the alkene. They are going to just copy down. All is going to happen is oxidative, is the cleavage that happens between carbon-carbon double bond. Next type of reaction that would generate ketone or aldehyde is hydration of alkyne. Hydration of alkyne, meaning you add water to the carbon-carbon double bond. So hydration, it's adding H and adding OH. Adding OH. So if you have CC, if you have a CC triple bond and you add H, based on Markovnikov rule, which carbon should take the hydrogen? Carbon 1 or carbon 2? Based on Markovnikov product. If you want to get the Markovnikov product, carbon, which carbon? For Markovnikov, which carbon should take the hydrogen? Because we say hydration, and in hydration, we are adding H and adding OH. That's for hydration. Okay, so these two things would happen. You're adding hydrogen and you're adding OH. My question is, which carbon will take the hydrogen? Carbon 1 or carbon 2? Which one would take the hydrogen? What is Markovnikov rule? That is it applies to addition reaction to the pi bond. When the pi bond breaks and you have like electrophile and nucleophile, like hydrogen and then hydroxide. Electrophile or hydrogen often is going to add to carbon with greater number of hydrogen. So in this case, we have one hydrogen, and carbon 2 has 0 hydrogen. So hydrogen will add to carbon 1, and OH will add to carbon 2. So when hydrogen adds to carbon 1 and OH adds to carbon 2, you break only one of the 2 pi bonds. So now you end up with enol. Enol, it's in and then OH group attached to it. It's the group is called enol because this carbon has carbon-carbon double bond, which is alkene. Same carbon carries both in and ol. It's also attached to OH. So it carries OH for alcohol and it carries CC double bond for alkene. So we have enol as the functional group. So when we have the enol is very unstable, okay? It's not isolated because it's very unstable. And is going to go through like tautomerization. And what is tautomerization? Is the basically a resonance that in this specific type of resonance is not only the pi bond and the pair of unshared electrons that they are moving, hydrogen also is going to move. So when hydrogen moves from OH to the other carbon, okay, so hydrogen from the OH moves to the other carbon, and then you get the C double bond here. So in Markovnikov addition, when enol is like OH is not on the first carbon, then you're going to get methyl ketone as a product. So this is one of the methods that you can prepare ketone, but specifically is going to give you methyl ketone. This is for Markovnikov addition. And for anti-Markovnikov hydration, your reagent, basically hydroboration oxidation of alkyne, this is anti-Markovnikov addition. For anti-Markovnikov addition, OH is going to add to the first carbon and H will add to carbon 2. This is anti-Markovnikov. We have enol functional group because this carbon carries both ol for alcohol and ene for alkene. So one carbon carries two functional group, you combine it and you have enol. Enol is not very stable and is going to go through a resonance, or a specific resonance type is called tautomerization. In tautomerization, hydrogen from OH will be transferred to the adjacent carbon, not to the same carbon that has the OH, but to the adjacent carbon. And then oxygen would change to double bond. So if the oxygen double bond is in carbon 1, now we have aldehyde as the functional group. So we have two hydrogen on carbon 2 and the double bond oxygen on carbon 1. So you get aldehyde. So you have to have, for this reaction, in order to prepare aldehyde or ketone, first of all, you must have alkyne, and your alkyne must be in terminal alkyne. As a result of Markovnikov addition of water, you would get methyl ketone because the OH is on the second carbon. The CO double bond is going to be assigned to the same carbon that has the OH. So if it's Markovnikov addition, OH would go to carbon 2, and the OH is going to change to CO double bond as a result of tautomerization. This is for terminal alkyne. If you have a terminal alkyne and you do hydroboration oxidation, that's adding water, anti-Markovnikov, OH will add to carbon 1. And if OH would add to carbon 1, this OH is going to later on, as a result of tautomerization, it would change to CO double bond, and then you move the hydrogen to the adjacent carbon. So you get aldehyde. Aldehyde is going to be produced. Now, what happens if you don't have terminal alkyne and if you have internal alkyne? What, as a review from Organic 1, when you have internal alkyne, if OH is added to the first carbon or second carbon, and it can go to, tautomerization as well, but it can be, you get mixture of two products. So you could get like ketone, either CO double bond on this carbon or CO double bond on the other carbon. So you don't get like specifically like a methyl ketone like you had for terminal alkyne, or you don't get aldehyde at all, because it doesn't matter if the OH is on carbon 1 or 2, or in this case, if this is carbon 1 to carbon 2 or carbon 3, still you are going to get ketone, not aldehyde. Questions? How would you prepare? So this is like a retrosynthesis. How would you prepare this ketone? What have you learned about preparing this ketone? Forget about or don't worry about this solution at this point. How can you prepare ketone based on what you learned so far? And which method can be used to prepare this ketone? I wait for your response before I move on. You want to make ketone. We've been talking about making ketone for at least 22 minutes. And can you tell me, how could you make ketone? Any response? How can you make ketone? No response? How can you make ketone from secondary alcohol? Can you change secondary alcohol to ketone? Can you hear me? Okay. PCC? Sorry, I didn't see the chat. I just, okay. PCC with secondary alcohol? Is that what your response is, Mohammed? PCC plus secondary alcohol. So what should be the secondary alcohol in order to make this ketone? What should be the secondary alcohol? Everything stays the same, right? Everything stays the same. It's 5 member, sorry. Everything stays the same with exceptions of here you have OH. So if you have a secondary alcohol and you add PCC, it would change to ketone. If you have secondary alcohol, you add sodium dichromate, you add sodium dichromate with sulfuric acid, you will get the ketone. Both strong and weak oxidizing agent works for oxidation of secondary alcohol to ketone. If the question says that you cannot have more than 6 carbon, because that's the instruction, and if I use this, I already have 5, 6, 12 carbon, then it's an answer, but it doesn't follow the instruction because the instruction says no more than 6 carbon. But I just wanted to make sure that you know, at least if you have a secondary alcohol, you can oxidize it to ketone, and the structure of the secondary alcohol with respect to ketone you have is just the single bond OH instead of the double bond O. Now, if you want to start with only 6 carbon, then you have to go with the first prepare secondary alcohol. So if you want to prepare secondary alcohol, you have to prepare secondary alcohol, you use Grignard reagent before, you use the alkyl lithium. So if you want to use Grignard, you can take one side of the molecule for Grignard and the other side as aldehyde. So you start with the 6 carbon aldehyde, and you have your Grignard. The magnesium is plus and this carbon is negative. It's unique because it's a strong nucleophile, and this nucleophile, it can attack the carbonyl group. Carbon in the carbonyl group, because it already has 4 bonds, when the new bond forms, the pi bond will break over the oxygen. You protonate that, and you get secondary alcohol. So Grignard plus aldehyde, it gives you secondary alcohol. Secondary alcohol, when it's oxidized, it will give you ketone. So the only restriction for us that we couldn't use this alcohol to begin with, even though it's one of the options, if you didn't have this restriction, is no more than 6 carbon. So you have to start with the pieces or build up the molecule, the secondary alcohol, before you can use this directly. So if you had no restrictions, you could just start with the secondary alcohol and oxidize. For the second compound, which is aldehyde, right? Is an aldehyde. And you want to make aldehyde restriction is you cannot have more than 6 carbon. So all you can do in this side, keep this 6 carbon here. And you have to add, you can use this as a Grignard. Grignard or organometallic compound is a good way to have a carbon-carbon bond. So you, in order to connect these two, you have to have one Grignard and then the other one, it could be like formaldehyde, it can be epoxide, it could be ketone, it could be ester or acid chloride. But you have to see your product is it's an aldehyde. If it's an aldehyde, one step prior to this, it must have been a primary alcohol. So basically, one of the last step that you have here, it should be this CH2 OH. Okay, so you have primary alcohol, and then from primary alcohol you add PCC to go to aldehyde. But we first need to make this primary alcohol. What are the 2 reactants that can give us this primary alcohol? We learned from chapter 10 and 11 that if you have Grignard reagent like this, again, you want only 6 carbon, MGBr, this is your Grignard reagent, plus what reagent can I use here? If I use formaldehyde, it would give me primary alcohol, but what about the second alcohol? If I use formaldehyde, it would give me the primary alcohol, but then I would be missing this carbon here. So in order to get 2 additional carbon, I have to use an epoxide. Okay. If I use epoxide, it can, this Grignard reagent, which is negative charge on the carbon as a nucleophile, it's going to attack the one of the carbons, and it doesn't matter which one. In this case, because it's symmetrical epoxide, the triangle would break over this oxygen. Then you protonate, and you get your primary alcohol. So the reagents that you have here, you want to make sure that you are using ether as the solvent, because you cannot use Grignard without the solvent of ether as a solvent. And then after you do the preparation, then you have to hydrolyze it. Okay, so you want to make sure always follow a Grignard reagent by hydrolysis. So you would hydrolyze it, and then it gives you primary alcohol. When you have primary alcohol, you have to be careful. You cannot use sodium dichromate because it's primary alcohol. And when you oxidize, you have to use PCC in order to keep it in the aldehyde functional group. Any questions? So since you have that restriction, you must start with like pieces of the molecule. But if you didn't have that restriction, you could have just start with the primary alcohol right here and say, well, as soon as, you know, I add PCC to this primary alcohol, I can get aldehyde. For the ketone, this ketone, because it's aromatic, the other method that we learned, further craft acylation. So you bring your acyl group from this acyl chloride compound. So basically you just copy the missing part, and then you add that to the benzene ring in presence of the aluminum chloride. And with the further craft acylation, you can get ketone. For the other one, we talked about this already, which is the Grignard plus epoxide. That gives you primary alcohol with addition of 2 carbon. Just you have to keep that in mind, that Grignard plus epoxide would give you primary alcohol with addition of 2 carbon, and then you use the PCC to get to the product. Now, if you have a acetanilide, okay, or you have the acetylene. Acetylene, the hydrogen from acetylene, this is coming from chapter 9. Hydrogen from acetylene is acidic. You can add a strong base like sodium amide, NaNH2, to terminal alkyne and remove the hydrogen. So when you remove the hydrogen, you end up with a nucleophile. So acetylenium ion that you have here, it can act as a nucleophile. It can react with alkyl halide. All you need to do is to be able to get a terminal alkyne with that number of carbons that you had. So you have 6 carbon from the alkyl halide. You have 2 carbon from the acetylene. And now you have a terminal alkyne. If you have terminal alkyne, how can you change that to aldehyde? You have to do hydration. You have to have OH on the first carbon. That means is the anti-Markovnikov addition. And for anti-Markovnikov addition, you need to know your reagents. So you have to add the OH to the first carbon. And when you add the OH to the first carbon based on tautomerization, it would change to aldehyde. So hydration of terminal alkyne with anti-Markovnikov reagent, it would generate the aldehyde. So with the synthesis, you have to just go back like one step at a time. See what would be the step just prior to the product that we have. Okay. Questions. So you have to be able to memorize all the reagents, know each reagent and the reaction individually, and then you have to be able to combine them whenever you need. Just pull a reaction that you learned before. You can add the number of carbon in the carbon chain using like organolithium or alkyl lithium or Grignard reagent, and then specifically Grignard reagent to give primary alcohol. You must know that if you add formaldehyde, it gives you addition of 1 carbon, but if you add epoxide, it would give you addition of 2 carbon. Those are very unique reactions. So you have to memorize it. And one way to be able to memorize and remember it for the exam is to make sure to do end of the chapter problems. There are a lot of end of chapter problems that you can do every other problem and use some of these reagents, because if you don't use them just one time, I explain it to you, if I used in 2-3 example is not going to be enough for you to be able to pull from the bank of the or database or the bank of the chemical reactions that you know, the time of the exam trying to put them together and get the synthesis reaction going. You can synthesize ketones from dithiones. Dithiones or 1,3-dithione, that's the structure. So you have this structure here. What you can do in this structure, you can remove one of these hydrogens. These hydrogens are acidic. You bring a base. The base that you are using to remove a hydrogen is going to be butyl lithium. What makes butyl lithium to be a good base? Because if butyl lithium removes the hydrogen from your compound, it's going to change to butane. So C4H9 would change to C4H10, which is a lot more stable. So C4H9 is a conjugate base to C4H10. C4H10 is a very weak acid, so the conjugate base is going to be strong base. So is it strong enough to remove hydrogen from dithiane? So your dithiane is like the 1,3-dithiane is part of the ring with respect to each other. These are the position of 1 and 3, and it makes these hydrogens like acidic hydrogen, so you can remove it. And when you remove it, you give this negative charge here. When you have the negative charge, by this time, especially I emphasize that like a couple times for previous slides, that if you have negative charge on carbon, how would you classify that carbon now? Is it a nucleophile or electrophile? Like anyhow, you remove a hydrogen and you give pair of electron to the carbon, carbon is negative charge. If the carbon is negatively charged, it's going to act as a nucleophile. So if you have a nucleophile, then it can attack nucleus. What are the popular nucleus? You could have the carbonyl compound, or you could have alkyl halide. So if you make this to attack alkyl halide, which is shown on this step here, your nucleophile is going to attack the alkyl halide, the leaving group would leave, and you replace one of the hydrogens with the R group. One thing you want to know that if you add this reagent to dithiane, so if I have hydrogens here, hydrogen, hydrogen, and I add that reagent of mercury chloride or mercury 2 chloride in acidic solution and water, if I hydrolyze this in presence of the mercury chloride, is going to change this carbon to CO double bond. That's what you get, which is formaldehyde. So the hydrolysis of dithiane is going to give you formaldehyde. Now, if you want aldehyde, before you hydrolyze it, you replace one of these hydrogens with R group. How do you replace the hydrogen with the R group? You have to remove the hydrogen. If you're removing hydrogen, you have to use a strong base, and the organic base that is proper to remove the hydrogen is the lithium or butyl lithium, and butyl lithium is going to remove the hydrogen. So if you remove the hydrogen here, then you want to replace with the R group, so you add alkyl halide. They're acting as a nucleophile. So a nucleophilic substitution reaction, leaving group would leave and R group would add. You hydrolyze in this step, you would get the CO double bond, one R group and one hydrogen. Can you tell me what would you do if you were going to make ketone? How would you change this reaction? Or how would you modify the steps if you want to get ketone? How would aldehyde be different from ketone? What do you think should be done? And I'm going to give you a hint. What should be done before this step? Before hydrolysis? If you replace one of the hydrogens, you get aldehyde. And if you want to get ketone, what needs to be done? before hydrolysis. Before hydrolysis, if you want to get ketone, before hydrolysis, before you do to this step, first you have to take this through other steps that you had and get to R group here. So basically you remove the hydrogen again by bringing another molecule of butyl lithium. You remove the hydrogen and then bring another RX or alkyl halide to replace the hydrogen with a second R. So if you have R group and then you add the mercury chloride with hydrogen and H2O, this is going to give you ketone. If you hydrolyze without taking any hydrogen, you would get formaldehyde. Hopefully you get it now. If not, go back and review it. If you hydrolyze dithiene or 1,3-dithiene without replacing any of the hydrogens, you would get formaldehyde. If you remove one of the hydrogens and then hydrolyze, basically it's this route here. You remove one of the hydrogen and then hydrolyze, you would get aldehyde. If you remove both hydrogens and replace with R group, then hydrolyze, you would get ketone. So you can get aldehyde, ketone, or formaldehyde from dithiene. Well, dithiene is not the only method, but is one of the methods. Just is showing here how to get ketone. So if you after you replace one of the R groups, you continue with second mole of butyl lithium and remove the hydrogen, bring a second alkyl halide, replace the other hydrogen with the R group, then hydrolyze it, you can get ketone. Okay. To replace the, to synthesize ketone from carboxylic acid, you can do substitution reaction. What is the substitution reaction? Here you have your alkyl or aryl lithium. When you have your phenyl lithium, the or organolithium, it doesn't have to be the phenyl group, any group would work. With the phenyl lithium, in this case, acting as a nucleophile. When nucleophile comes in and attacks the carbonyl group, if there is no leaving group, pi bond will break over the oxygen. We learned that in chapter 10. But since there is a leaving group, the leaving group is going to leave, and then you end up with formation of ketone. Okay. What I said is about like overall reaction. So the nucleophile is going to come in and replace the leaving group. So this is the leaving group, is OH would leave, and you bring the nucleophile. Is a nucleophilic substitution reaction, overall reaction. What is shown here is basically the mechanism, which says the same thing, and that's what we are more concerned about. The reaction, the overall reaction. Your nucleophile is going to form bond with the carbonyl group, leaving group would leave, and you end up with ketone. So as long as you know the overall reaction, you should be fine. Before looking at this reaction, I want you to have, you have CC triple bond, okay? You have CN triple bond. You hydrolyze it, H2O. In acidic solution, you will get carboxylic acid. If you have CN double bond and you hydrolyze it, it would change to CO double bond. Okay. So just keep this in mind. If you have nitrile and you hydrolyze it, you add water or hydrolyze an acidic solution, you would get carboxylic acid. But if you have imine, which is a CN double bond, imine, a CN double bond, if you hydrolyze, it will change to CO double bond. Now, if you have nitriles, you don't want to get carboxylic acid, what can you do to change this one to double bond first? You can bring a Grignard reagent. Grignard reagent, carbon is negative, magnesium is positive. So from the carbon, from the Grignard reagent, the carbon attached to the magnesium, which carries the negative charge, with nucleophile, is going to form bond with the carbon that is positively charged. So this is a partially positive carbon because nitrogen is pulling electron away. In this case, when the Grignard comes in and forms bond with the nucleus or the carbon with the positive charge, there are two cases. Either you have leaving group or there is no leaving group. Nitrogen is not a good leaving group and R is not a good leaving group. So if there is no leaving group, a pi bond will break. So CN triple bond would change to CN double bond. Now, what happens if you have a CN double bond and you hydrolyze it? As soon as you add the water, when you hydrolyze it, it's going to change the CO double bond to CO double bond. So you had one R group already in the nitrile. By bringing Grignard reagent, you did replace or add another R group to this carbon, and then CN double bond. The CN double bond, if you hydrolyze it, it would change to CO double bond. You need to be familiar with all of these methods of preparation, but you need to memorize few of them like by heart. So if someone tells you, okay, prepare this ketone, you don't say, well, I don't know how to prepare it. I learned like too many methods that I don't remember any of them. So you have to know a couple of them like by heart, that you can prepare the ketone on the paper at least, or in the lab, and then be familiar with the rest of them. Okay. And the reagents that is needed for each of the experiments or each of the reactions and the number of steps, it's different from one reaction to another reaction. But some key points that if you have a CN double bond, you hydrolyze, it would change to CO double bond. This can help you actually. Well, say I have CN triple bond. If I hydrolyze it, it's going to give me carboxylic acid. So I don't want to make carboxylic acid. What I need to do now is to change the CN triple bond to CN double bond first. You can't just break the pi bond. You have to bring a nucleophile or something to add to this carbon in order to break the pi bond. So Grignard plus the nitrile group, it can change it to imine or salt of the imine, and then you hydrolyze it, it will change to CO double bond. Acid chlorides can be reduced, okay? If you reduce this using LAH or lithium aluminum hydride. We learned about this in chapter 11. At the same time that we learn about sodium borohydride, weak, and this is the strong reducing agent, weak reducing agent. Our weak reducing agent is not going to reduce acid chloride because it can be used only for aldehydes and ketones. It can reduce the aldehyde to primary alcohol, sodium borohydride, and sodium borohydride can reduce ketone to secondary alcohol. When it comes to LAH or lithium aluminum hydride, it's strong. If you use very strong, and we use this in the chapter 11 again, when we were preparing primary alcohol, if you use this, it would change to acid chloride, would change to primary alcohol. Well, we want to reduce it, but we don't want to reduce it all the way to primary alcohol. We want to keep it in the aldehyde stage, because from aldehyde, if you reduce this further, it will go to OH. Okay. So we don't want to do this. We want to keep it in the aldehyde. So what we are going to do to LAH, we have to poison the LAH. How do you poison LAH? If you compare the structures, lithium stays, aluminum stays, one of the hydrogen would stay, but the other hydrogen, the other 3 hydrogen is going to be replaced by bulky alkoxide group. T-butoxide or T-butoxide, a bulky alkoxide group replacing the other 3 hydrogen. Because if you have 4 hydrogen is going to be very strong reducing agent. You are removing 3 of them, you are only leaving 1. That basically is called, the term is called like poisoning the reducing agent. You are going to make the strong reducing agent, change it to mild reducing agent. So if you have mild reducing agent, is going to reduce acid chloride to aldehyde and is not going to go to primary alcohol. So you can get the reduction of acid chloride to aldehyde. That's another method for preparation of aldehyde. Okay. Gilman reagent R2CuLi. You need to know about the Gilman, something about the Gilman reagent. Gilman reagent, it's very similar to RMGX, and it's very similar to RLi. What is the similarity? In either one of them, the metal is positive and the carbon attached to it is going to be negative. So metal is positive, the carbon attached to it is negative, this is positive and negative. So all of these, it can act as a nucleophile, very good nucleophile that has carbon, okay, or is a carbon chain that acting as a nucleophile. Nucleophile can attack a nucleus, okay, can attack the nucleus, or carbon with the positive charge. So this is the similarity. All of them, okay, all of them, they are acting as nucleophile. The difference is that the Grignard reagent is much stronger than R2CuLi, is stronger. Now, if this is a stronger, what's going to happen if it's a very strong nucleophile means that it can go 2-step. So instead of the Gilman reagent, if you add the Grignard reagent, it's not going to stop here because you have ketone plus RMGX, which is Grignard, it will give you tertiary alcohol. But if you use Gilman reagent, nucleophile comes in, leaving group would leave. So you get one of the R groups replacing the chlorine, and now you have your ketone. Because Gilman reagent is weaker than Grignard, it will stop in the first step of substitution. If you use Grignard can continue this reaction and it can change to tertiary alcohol. So Gilman reagents would only transfer one alkyl group of the Gilman reagent and replace it with chlorine. That's a method for preparation of ketone from acid chloride. So far, all of the reactions that we talked about, they were preparation of either aldehyde or ketone. And even though they are covered in the PowerPoint, they are recorded in the video lecture. What would be best for you to take a piece of paper and list reactions that you can prepare aldehyde, list all the reactions that is covered in this chapter, and you can prepare ketone. Make sure you know the reagents, you know what's the reactant, what's the reagent, what is the product, because it's very important to learn about how to prepare aldehydes and ketones, because preparing aldehydes and ketones, it can actually act as a reaction for alcohols, like some of them, or reaction for carboxylic acid or acid derivatives. So even though you're only studying these as the preparation method, but it covers reaction for other compounds, for at least for the oxidation reduction type reactions. So it's preparation for one, but chemical reaction for others. The next slide, it starts talking about reactions of aldehydes and ketones. What type of reaction do you expect from aldehydes and ketones? Just do one quick thing here. Reactions of aldehydes and ketones, it can involve like the addition reaction, because CO double bond contains one sigma bond and one pi bond. So it's one sigma and one pi bond. So you can break the pi bond just like CC double bond. When you have one sigma and one pi bond, you can break a pi bond and then add two groups to the carbon. You add electrophile and you add nucleophile. In this case, also, you are breaking a pi bond. When you break a pi bond, you add electrophile and you add electrophile and add nucleophile. Okay, but for CO, it's kind of more obvious. Where would the electrophile go? Where would the nucleophile go? Because the bond is a polar bond. Oxygen has two pairs of unshared electrons. So if you have your electrophile, has a more tendency to go to the oxygen. And nucleophile, because as nucleophile has either extra electron or has a negative charge, it would attach to the carbon. So if you're adding a nuc-H, meaning that nucleophile, and then this is like electrophile would add to the oxygen, nucleophile would add to carbon, because the bond is a polar bond. Now, which one is going to come in first? Would the electrophile come in first or the nucleophile comes in first? It depends. Do you bring like a strong nucleophile? Then the nucleophile comes in first. Are you going to bring like a catalyst, like a H+ or acid? Then electrophile would come in first. So the order of which one is going to add it depends on the nature and the nature of the reactants that you have, the nucleophile and the electrophile. One of the reactions of the aldehydes and ketones, which everybody loves, like especially, I know you're not preparing for the MCAT or PCAT or whatever, ACS, but this reaction is very popular. The reason is popular because just like bringing the Grignard reagent that adds the number of carbon in the carbon chain. It increases the number of carbon in the carbon chain. It's very similar. This type of reaction is known as like condensation reaction. When you have condensation reaction, like esterification is acid plus alcohol, you bring two molecules together and you make one molecule of ester. It's kind of condensation reaction with the loss of like a small inorganic product. Reaction of Grignard with carbonyl group is condensation reaction also, because you're bringing like one Grignard, which is originally coming from alkyl halide, and then you have aldehyde or ketone, and you end up with alcohol with greater number of carbons. So if your aldehyde has 2 carbon and the Grignard has 2 carbon, the final product is going to have like 4 carbon. So it's a big deal to be able to start with 2 carbon and end up with 6 carbon in organic chemistry, because the opposite it's been very popular. So basically you take the oil and you get the olefins and you get the carbon chain, like from gas, from the oil product from the living organisms. The remaining of the living organisms, you would extract it. You would extract the gasoline. You can break it, and then you make smaller molecules, or you burn it, or you cut in pieces. That's like killing the resources that you have of the human remaining, or I'm sorry, living organism remaining. But when it comes to bringing smaller molecules together and making larger molecule, people, the scientists, they got like Nobel Prize for this type of reactions, being able to condense 2 molecules together. What you want to know about Wittig reaction? First of all, you need to know that the CO double bond is going to change to CC double bond. I kind of make it simplify this, okay? I simplify it. So CO double bond changes to CC double bond. The CC double bond, one side of the CC double bond is coming from the CO double bond. The other side is coming from alkyl halide. Okay, so it's basically the alkyl halide plus the carbonyl. That gives you CC double bond. Now, you don't add the ketone or aldehyde to alkyl halide directly. You have to first change the alkyl halide to, you have to change the alkyl halide to proper reagent, which is called Aldehyde. Aldehyde is this complex here. You have the carbon with the negative charge. So Aldehyde would act as a nucleophile and is going to attack this carbon. How do you change the alkyl halide to Aldehyde? Is you are going to make the alkyl halide to react with triphenylphosphine. This pH, small pHs, those are phenyl groups. So basically, if you were going to draw it, it would have been like 3 large phenyl groups attached to it. So if it's simplified, okay, so triphenylphosphine, this is the same thing as PH3P. So when you make this, when you bring the triphenylphosphine plus the alkyl halide, the phosphine with pair of electron acts as a nucleophile and is going to form a new bond between the nucleophile and the carbon, positively charged carbon. Leaving group would leave. So you have this complex here. So you have the salt of the benzyl triphenyl phosphonium salt. Now, from here, you bring a base again. I'm saying we are using the same base one more time. Butyl lithium is a base. Why is a base? Because if it takes the hydrogen, it's going to change to butane and is stable. So it's acting as a base. So know the butyl lithium as a base, strong organic base. This is going to remove a hydrogen from the alkyl group. Okay, when it removes a hydrogen, it's going to leave the electrons back, so the carbon is going to gain a negative charge. So this complex is the Aldehyde that you need. Aldehyde acts as a nucleophile, and the nucleophile would attack the carbonyl group. So when the nucleophile attacks the carbonyl group, there is going to be like a rearrangement. So it's going to be rearrangement, and you would see that the triphenyl phosphine is going to combine with the oxygen, and it gives a byproduct. This byproduct will be produced. This byproduct, and then this 2 carbon is going to form a double bond because both of them are missing a new bond or missing one of their bonds. They are not happy with 3 bonds, so it's going to form a double bond. So the double bond, how these 2 are going to combine, because there is a negative and positive charge and they are close enough to one another, is going to form a bond. And then when there is when that bond forms, then internal rearrangement, basically they are going to come to agreement that is going to leave, and the carbon-carbon double bond would form. Now, what part you need to know is how to make the Aldehyde, because this part of the mechanism, the rearrangement, you don't need to know the mechanism for this part, but you need to know what is your reactant, what's your product, and also the mechanism for how to make the Aldehyde. So basically this part of the reaction or the mechanism, you need to know how to make the Aldehyde, because you need to know the Aldehyde is coming from the alkyl halide, and you have to add the triphenyl phosphine to prepare your alkyl halide as a nucleophile, because alkyl halide is not a nucleophile. Why is not a nucleophile? Let's then imagine ethyl bromide. Ethyl bromide, Br is slightly negative, this is slightly positive. So this cannot act as a nucleophile. So it's not a nucleophile. But you can change this to a nucleophile. How can you change this to nucleophile? You combine it with triphenyl phosphine. Then remove a hydrogen. When you combine with triphenyl phosphine, remove a hydrogen, then you are going to make that a Aldehyde. An Aldehyde, meaning that it's missing a hydrogen and also has a pair of unshared electron or has negative charge. So chloride has a pair of electrons or negative charge, you call it IDE. Methyl is missing hydrogen, so it gains ill. When you say Aldehyde, meaning that it's missing a hydrogen, but it has negative charge. So you have your Aldehyde. How to go from alkyl halide to Aldehyde, you need to know that, the steps. So I'm not saying don't worry about all the steps, just saying you need to know some of these steps, but how to, this part you don't have to know. You don't have to memorize, you don't have to do, even though it's like when you get these formation of the nucleophile with the carbon, pi bond is going to break over the oxygen. It's not hard to understand it, but I'm saying that it's not the main concern. The main concern is to be able to generate the Aldehyde and then bring and react it with the CO double bond or with the aldehyde and ketone. The net result is formation of carbon-carbon double bond, which one part of the molecule is coming from ketone or aldehyde, and the other part of the molecule is coming from alkyl halide. So one side is coming from alkyl halide, the other side is coming from the aldehyde or ketone. Okay, so if the question emphasizes that you have to use a Wittig reagent, so you just have to cut through carbon-carbon double bond, know that one side is coming from aldehyde or ketone. So you can take this side and add two oxygen, add double bond oxygen. So you have your aldehyde. The other side is coming from Aldehyde. Okay. The other side is coming from Aldehyde, and you get your the other side from the Aldehyde. So you have the two choices. So one side is coming from Aldehyde, the other side is coming from aldehyde or the ketone. In one of the steps, you want to make sure that you have a primary alkyl halide, because when you add the phosphine, triphenylphosphine is an SN2 type reaction. So if it's an SN2 type reaction, you want to have primary alkyl halide. So that's the only thing you have to be careful. So if you're getting your alkyl halide, you want to make sure that your alkyl halide is a primary alkyl halide. That would help you to pick the proper alkyl halide. Otherwise, you have two choices and you can use either side. Okay, it is